you can kind of see, whoa. I think you can get the point here. I can't zoom in anymore, but you see we still have error, right? But it's less error. And so what would really work for us here is if there was a way that maybe we could get even more triangles in there. So I've got to make the triangle smaller, don't I? So those are even smaller triangles, which means I'd need more of them, right? And so someone would sit there, and try on a piece of paper with as straight of an edge as they could get, and they would get really, really, really small triangles in there, or sometimes they would use rectangles. It just depends. They would use different things, or polygons, and they would try and figure out a way. And what happened is they were able to get really, really close.
They got exhausted and just put a number.
And then they get exhausted, and then they get to something that they all were comfortable with. And I believe the one that they really liked to use was 22/7. They used that for pi for a long time because it was close enough for what they were doing. So instead of saying the area is pi r squared, what is 22 divided by 7 on your calculator? 3.14, and pi is close to 3.14, right? In fact, most of the time that you do calculations in math classes, they say just use 3.14, right? So this was good enough for a lot, but it wasn't the exact area. They knew that it was pi, or the real area was not going to be found using this. Okay? Understand? But the method of exhaustion of coming up with this smaller and smaller triangles is really where we're headed here. Okay? Because theoretically, how would you find the true area? You would take each triangle, and what would you let happen? You would shrink it down until what? Until it closes up to a single line. And then you take every single line, and wouldn't you get the true area? What's the problem with that? A line has no area, right? A line has no area. So it would be a double problem, because if you let the triangle come to a line, you have no area, and you would have infinitely many of them, wouldn't you? And you can't add up an infinitely many number of things, can you? Or can you? And that's what Newton and calculus was able to figure out, is that there's still a way to do this to get the exact answer, but it's going to require something from Cal 1, the limit. Right? The limit allowed us to go and send a number to a certain place without actually ever getting there, right? And that's exactly what we're going to do here. We're going to let the number of those go to infinity. If we let the number of triangles go to infinity, that's equivalent to saying letting their angle come down to 0, wouldn't it? But it's a limit, so we know we can get answers with limits. All right, so this was, that's just another picture. Now, before I proceed, I wanted to have you remember that there is a formula from pre-cal for the area of a triangle. Everyone just told me area equals 1/2 base times height for a triangle? Yes? So is this one? Someone gives you a triangle. If you know the height and you know the base, you know that the area is 1/2 base times height. But that formula, does anyone here remember seeing that one? 1/2 area is 1/2 AB sine theta. This formula is a little more powerful. I just wanted to remind everyone of it. If you come to a triangle like this, a lot of times you don't know the height of a triangle. A lot of times you know two of the sides. So like this side here, I'll call it A, and this side right here, I'll call it B, which will also be the base. If you know the angle between them, theta, then the area of the triangle changes to that formula. Nobody remembers this from pre-cal? So most people think that this formula is like magic or something, right? But check this out real quick. What is sine of theta? Everyone tell me right now, what's sine of theta? Sine of theta is what? H over A. Solve for H. A sine theta. Agreed? Rewrite this formula. Replace H with A sine theta. And what do you get? That formula, right? So all this is just an application of redrawing your triangle and coming up with the relationship. And all right. So when they were trying to find, the reason I put that up there is because when they were trying to find the area of the circle, and let's say we had a cut here, and I'm trying to find the area of that triangle right there. If I knew the angle and I knew the radius, wouldn't that be the same as having this angle and A and B would be the same number? Yes, A and B are the same number. So R and R basically. And so they could find the area with that formula really easily. I'm just showing you that. I just want you to see that. And that's how they could get the calculation quickly. And how would they know the angle? Well, if they say I'm going to cut it into 4 triangles, what would the angle of each one be? 90, right? So that's 360 divided by 4, that's 90. If they decided to cut it into, let's say, 45, right? This would be 8 triangles. So that would be 45. So they could keep doing that over and over and over and over and over, right? All right. Now, with all that in mind, okay, the idea that if you want to try and find the area of something that is complicated, that you can do this thing where you add things up and add more and more and more and more of them and then try and get an area that way. Let's take a look at this distance problem. Ron, what's going on there, buddy?
I remember all this.
What's that?
I remember everything
You remember everything?
from Riemann Sums.
So that gives you the authority and right to just text on your phone and chill out in here? If you know it, you can leave. I mean, I have no problem if you leave and go outside and text or, go home and text, just not in here. Okay? All right, so let's say a person walks at a constant speed of 2 miles per hour. Maybe you shouldn't have sat in the front. Maybe you should have taken that seat in the back. I may not have seen you.
I offered it.
I know, right? Ron messed up. Got called out. All right, so let's say a person walks at a constant speed of 2 miles per hour. And what we're going to do is we're going to plot time versus speed. Right? So, constant speed. Go ahead. Hurry up. I don't think I've ever had anyone take me up on that. Wow. I think that's the first time anyone has ever accepted the option to leave. All right, I'll take attendance here in a second. All right, so would you agree that a person walks at a constant speed of 2 miles per hour? That would be the graph of their speed. Look, I'm plotting speed, right? So speed is 2 miles per hour, so at every point in time, their speed is 2 miles per hour. How far have they gone in 3 hours? So let's say this is time 1, 2, 3 hours. They've gone 6 miles? Would everyone agree with that? How does that tie into this picture?
The area.
It's the area. Look, if you create a rectangle going from 0 to 3 and go straight up to the actual graph, and you look at the area of this rectangle, the area of that rectangle is 6, isn't it? The area of this is 6. Is it coincidentally that it's also how far they walked, or is that the way it will always be? What do you think? Do you think that if you have speed here and you have time here, that the area underneath the curve on that time interval will always represent the distance What do you think? Or was it coincidence? What do you think?
Always.
It's always going to be that way. All right? It's always going to be that way. Now, why? Well, just think about if I took just a slice of this. Imagine I just take a slice of this, right? Just take a little slice of it. Would you agree that the width of this slice is a measurement of time? Yes? This is a time measurement. And do you agree that the height of this slice is a measurement of what? Speed? And do you agree that when I do area, I do time times speed? Time times speed. Right? And we have the classic formula from physics that what? Well, there's a couple of them. That relates time, speed, and what is the definition of speed? Speed is distance over time, right? So if I multiply both sides by time, distance is time times speed. So this has got to be a measurement of distance, right? So this little area is the measurement of how far I went on that little sliver of time. Agreed? And if you add them all up, that gives me the total distance I traveled. Okay? Now let's look at another problem similar to this. How far does this person go between the hours 2 and hours 5? So we have a different picture. This time, I'm not telling you what their speed is. You have to look at the graph. I'm sorry, I need to... silence this thing. So we have something like this. It looks like, does that look like one, two? I can't even tell. Between 2 and 5. Are we going to say up here at 2 it's at 1? Is that good enough for you?
Yeah.
Okay. So at 2, I'm up here at 1. And then at 5, where do y'all think I am at 5? Up at 3? Yes? So in this case, I only want the distance traveled between the 2nd and 5th hours. So I want this distance between here and here, right? Which we just said should be the area underneath that curve, which would be everything in here, right? So how would you find that area? How would you do it?
Divide. There can be a line where dividing it into a triangle.
Okay, so you want me to actually split it into 2, make a rectangle here, call it R, and then make this one a triangle T, then find the area of the rectangle, then find the area of the triangle, and then add the 2 together? Right? You could do that. What would the area of the rectangle be? So how tall is it? How wide is it? 3. 1 times 3, right? So this would be 3. And then what would the area of this one be? So how tall is it? 2. How wide is it? 3. So 2 times 3 is 6, but then half, right? Because triangle's half. So that's also 3. So what would the total distance be? 6. Was it miles? Was that the same answer as the one before or no? It was, right? Just coincidentally. But the most general idea here is just that it appears that if we can find the area underneath the curve, that can have very, very, like real, what's the word I'm looking for? I guess application, but it can be tied to physical quantities and it can have meaning, right? It can have actual meaning. Rather than just, oh, cool, we found the area underneath the curve.
Relational value.
What's that?
Relational value.
Yeah, relational value. Yes, I like that. All right, so how about this one? I'm going to make this a little bigger so you can see this. This time I actually gave you the function. I said, how far does a person go between hours 0 and 3? So here's the curve. I even tell you that the curve is f of x equals x squared. And at 3 and at 0, we all know that at 3, x squared is 9, right? So we need to find the volume. We need to find the area underneath this curve, don't we? What's the problem, though? It's curved, right? This is curved. This is not a triangle. We can't create a triangle, right? So how are we going to do this? With an integral somehow, yeah, but we don't know that yet. We're acting like we don't know that, right? Somehow this has got to be done, right? So we're stuck. So Riemann was a mathematician who was first to come up with an actual attack for something like this. And he called it Riemann Sums, or we call it Riemann Sums today. And it was just a way of generally trying to attack a function by approximating it with a bunch of rectangles. So take a look at this picture here. We need an efficient way of determining the area under functions. We use areas of rectangles. And I think I have a better animation here. Yep, there it is. So I did show you this, right? Okay. So what I want you to see right now is the blue curve is x squared, right? That's x squared, even though it doesn't really look like it.
Bless you.
And what I'm doing is I'm approximating x squared with one rectangle. So I'm going to sit here and I'm going to measure the width right here, and then the height the whole way up, and measure that. And that area is going to be what? How wide is this? This is 4 wide, right? 5 minus 1, that's 4 units wide. How tall is it? 5 squared is 25. So it's 4 wide, 25 tall. So the area of this entire rectangle would be 100. That's way over what it should be, right? The true area under that blue curve, that's an overestimate. So what I can do instead of using one rectangle, whoa, what the heck? Is I can use 2 rectangles. And this time, instead of going all the way across, I'm going to go halfway, right? Halfway, I'll go straight up, over, and then find the area of that rectangle. On this one, straight up, over, find the area of that rectangle. Add those 2 up, and that'll be an approximation, right? And the computer's actually doing it for us right here. We get 68. Can y'all see 68 right there? But again, that's too much. The true area is 41.333. And we'll talk about how we get that in a minute. I could do 3 rectangles, 4 rectangles, 5 rectangles, 6, 7, 8. And look what happens. The area is getting closer and closer to the true area, right? My error is getting smaller and smaller and smaller with each rectangle. Yes? Now, I could really make this draw out quite a bit. We only have 20 minutes left. And we could actually practice doing Riemann sums by hand. And they become very, very tedious. There's a lot of messy stuff inside of Riemann sums. And you learn how to do these, and then you come up with exact answers. But, and this is the formula for it, actually. It's this limit right here. All right, it looks pretty nasty, but it's doable. But do you see something over here? Do you see this? The integral. The integral. And that's what I want to get to. I'm going to skip over us doing Riemann sums by hands. It's going to be too much work. And time-wise, I'd rather us have more time for Chapter 8. So, but do you understand physically, geometrically, the problem? Yes, trying to find areas? So what Riemann sums says is that if you have some arbitrary curve, all right, and if you are able to take an arbitrary rectangle in here like this, okay, this is the function f, then what I need to be able to do to find the true area is I need to add up, right? I need to add up a bunch of rectangles. And for mathematical purposes, we like to use summations to represent add up. I'd like to add up the areas. How wide is the area of this triangle? Well, would you agree that, this rectangle, would you agree that each rectangle would have the same width? If I do an equal number of them, the same width? I'm going to call that delta x. Delta x means what? Change in x, right? The distance traveled, a change in x. So this change in x is going to be the same for every single rectangle, won't it? Yes? The height of the rectangle is never the same, is it? It changes throughout as you move from left to right, doesn't it? So the height of the rectangle will always be the function's value at that point, right? So I need to add up the areas. We just said that the area is the height of the rectangle, that's the height, times the width of the rectangle, which we said is what? Delta x. Understand what this formula means? Height of rectangle, width of rectangle. To get together, that's the area. I need to add them up. Then I need there to be an infinite number of them, right? I need to let the number of these go to infinity. So I need to somehow let the number of rectangles go to infinity. And what it was, the big fundamental theorem of calculus, that's what it's called, the fundamental theorem of calculus, says that guess what? If you actually want to know what this limit is, you need to be able to find the antiderivative of the function. And I'm not going to prove the fundamental theorem of calculus in here. But this turns into this. Now let's see if we can see why it is that this becomes this. Do you see now that the f of x is actually just the height of the rectangle? Do you see that the dx is what happens when the width of the rectangles become infinitesimally small? Okay, but it's still the width of a rectangle. The integral sign takes the place of the limit because we let the number of them go to infinity. And so I'm trying to get you, I guess, to see that every time you look at an integral, these pieces are usually connected to some geometric picture. And that's going to help you later, because we're going to be rotating these things around the axis and spinning them around, and then you're going to be creating volumes, and you're going to be looking at disks and cylinders, and you're going to be like, okay, well, how does that change this formula? Well, if you know the formula for a cylinder, then it just changes the formula in here. So we need to understand that these two are no longer just arbitrary function dx. It's actually width and height of a rectangle. I hope you're following this. So where do the numbers come in? Where do these numbers a and b come into the play? Well, a and b are the points where you want to start and you want to stop. So if you want to start at x equals a and end at x equals b, then we put a and b here, starting and stopping point. Now, I have 15 minutes. Y'all look like everyone looks demoralized. Should I not have kicked Ron out? Or have you? I didn't kick him out. He left, right? He chose to leave. Everyone's like, man, I should break out my phone so I can get out of here. All right, let's get back to this question. Find the area under f of x equals x squared on, what was it, 0 to 3, was it? Yeah. Yeah, it was 0, 3. On 0, 3. So we're going to be using some new notation here. We're going to be using what's called the fundamental theorem of calculus, which is also referred to, this version of it is called the evaluation theorem. And it says that if you want to know the area under this function, then of course you're going to come in, you're going to add up an infinite number of rectangles, aren't you? Each of those rectangles is going to be how tall? The function, x squared, times the width of each rectangle, which is going to be the same for every rectangle. It's going to be that little infinitesimally small thing, which we always call dx. This is called the differential. We have always known it as the thing that keeps track of our variable, right? But now this has geometric meaning. Then we use 0 and 3 to tell us where to start and where to stop, right? According to the evaluation theorem, the answer to this, all right, will be equal to, and I'm going to write the evaluation theorem up here. What was capital F? If this was little f, what was capital F? The antiderivative, right? That's the antiderivative. So what this says, the evaluation theorem says, what I need to do is just write down, right here, write down the antiderivative of x squared, of this right here. What's the antiderivative of x squared? 1/3 x cubed. Okay? Then draw this little line next to it, and then put the a on the bottom, which was 0, and then put the b on the top, which was 3. Now, all this is, in the evaluation theorem, is just a place for you to write the antiderivative down. That's all it is. This is just a place for you to write it down, and then for you to put the numbers here to keep track of your two endpoints where you're starting and stopping, right? That's what that is. Then the next part equals this right here, means you take capital F, which is this, right? And you plug what into it? B, which for us is what? 3. So what I'm going to do now is I'm going to set up a set of parentheses. That's for this one. Then I'm going to subtract from that this one, capital F of A. So I plug 3 into here. I get 1/3 times 3 cubed minus, the next one will be 1/3 times what? 0 cubed. And this goes away. And what's 3 cubed? 27 divided by 3? 9. And that's it, right? That's it. And the fundamental theorem of calculus and the evaluation theorem says if you want to find the area underneath the curve between 2 points, all you have to do is be able to find the antiderivative. If you can find the it's a perfect segue. Find the antiderivative. All you need to do is find the antiderivative, right? Once you do that, you plug in your 2 endpoints. Be careful though, because it's always the b first, then subtract the a. It's not the other way around, right? That number miraculously is the area under the curve. Yes.
Is the f of b minus f of a just supposed to be the delta x in the fundamental theorem?
Is it supposed to be the delta x?
Yeah, like or the limit n to infinity summation f of x.
All that stuff? Is it? I'm not quite following you. Like this? Oh no, in this formula, is it this part? Is that what you're saying?
Well, because what we wrote earlier on that curve you drew, the limit n to infinity and then summation f of x times delta x.
Yes.
Is that supposed to be the, like delta x part there? Or I don't know.
No, all that is, this right here is the notation that we use to represent that whole entire limit. Okay? This integral sign is the thing that's saying limit going to, because if it was just add up, I just, why not just use a sum? The integral sign is special in the sense that it's a sum, but it's a sum of an infinite number of pieces that are getting, right? Each of those rectangles is getting more narrow, more narrow, more narrow. So it's just a special symbol for that crazy looking limit.
Thank you.
All right, you're welcome. So this opens up the possibility of, You can, anything you can integrate, you can find areas under, right? Anything you can integrate. I like this one. Let's do this one. Find the area under cosine x between 0 and 2 pi. Find area under f of x equals cosine x on the interval 0, 2 pi.
Did you break it up?
We could, yes. We'll talk about that in a second. Let's just try and apply the fundamental theorem real quick. Also, let me just say, the Riemann Sums thing, it's, I've spared you quite the torture with Riemann Sums, okay? Riemann Sums is it's kind of a nightmare when it comes to just algebra, putting things together. It's tedious, but if anyone wants to see how to do it by hand, please just talk to me. Be happy to share it with you. Some people like that sort of thing. All right, find the area under the curve. So that means I need an integral, right? I need to set up an integral, and the height of each of the rectangles should be cosine x, the function, dx. So dx is still always going to be there because the width's always going to be dx. What are the numbers I put here? 0 and 2 pi. And then equals. So I just need to be able to find the antiderivative. Antiderivative of cosine x is just sine x, and then 0, and then 2 pi, right? That's the notation we use. Just write down the antiderivative, write down the two endpoints. And then I'm going to plug in and get an answer. Which do I plug in first? 2 pi. So sine of 2 pi, and then sine of 0 here. What is sine of 2 pi? 0. And sine of 0 is 0. So you get 0. But I know cosine has area, right? It has area under it. It does, doesn't it? I mean, let me graph it. That's what cosine looks like, doesn't it? So how is this, why is this telling me 0? It cancels out. It actually, it's counting this area right here as positive area. And somehow it's counting this other stuff as negative area. And then this is positive area. And because of the symmetry of the graph, the red part below is equal to the black part above, and then it's going to cancel out and get 0, right? Now, why is it counting it as negative? Imagine a rectangle. If I drew a rectangle right here, the width would be dx, right? What would the height be? Didn't we say it was the value of the function? And isn't the function negative down there? So it's going to count that rectangle as negative. Even though we know areas can't be negative, it doesn't know that, right? It doesn't know that the function can't be negative. So this could be dangerous, couldn't it? So that means we're still going to have some understanding of what the graph looks like to find an area, because if it dips below the x-axis, we're going to need to somehow account for that somehow, right? So what would be a better way of doing this problem if we wanted to find the true area under this? How could we do it? How do you think we could do this? Split it up, right? Like first go from 0 to whatever this is, then go from here to here, and then from here to here. So what are those numbers? Where are those occurring? Pi over 2 and 3 pi over 2. That would only give you this top piece, right? I'm not sure. You're saying go from here? You're saying just find out what this is from here to here? I'm not following you. That's.
And I guess erase the end part, the third part? Yeah, attach that.
Oh, okay. You mean move that over here? Yes, you could use the symmetry of this graph against itself. In fact, you could just find one of these, right? And then multiply times 4. Because there's 1, cut this in half, 2, 3, 4 of them. That would be your answer. But not all graphs are going to be nice and symmetric like this. So the standard protocol would be to break it up in different pieces. So instead of doing this integral that we just had, if we want to find the true area, our integrals would look more like this. We would do first an integral that goes from 0 to pi over 2 of cosine x, right? That would take care of this piece. Then what about this piece? We know that if we go from pi over 2 to 3 pi over 2, we know that that answer is going to come out to be negative, right? So instead of adding it, we're going to do what? Subtract it, because I know this answer is going to be negative. And so when I subtract a negative, it's going to become plus. And this one would go from pi over 2 to 3 pi over 2. I'm sorry? How do you graph cosine? My graph may not be that great. Where's cosine 0? Right? That's what this is saying? Where's cosine 0? Where's cosine 0? 90 degrees and 270, pi over 2 and 3 pi over 2. You following? Right, this is the cosine curve, right? I want to know where it hits the x-axis. It's at those 2 points.
So
Yes.
with a graph that's kind of not as nice, would we just use those points as our zeros?
You would have to find the x-intercepts of the graph. Yeah.
Yeah.
Yep. So you'd have to set the function equal to 0 to start, figure out where those are, and then you'd have to break up your integrals. I'm going to have a total of 3 integrals here. But I want to make sure everyone's okay with where I'm getting these numbers from. Okay. And the last one, what should I say here? Plus or minus? Plus, integral where to where? 3 pi over 2 to 2 pi of cosine x. I'll let you finish this one out yourself. But look, all 3 of these have the same antiderivatives, don't they? Antiderivative of all of those is sine. The only difference between these 3 integrals is that at this one you're going to evaluate it at these 2 endpoints. And then on this one you're going to evaluate at these 2 endpoints. Here, these 2 endpoints. And when you put this all together, you should get a positive number. I believe it's 2, but I could be wrong. Let's see if I don't think I did it here. No, I didn't.
Is
Okay.
there a negative sign over here because it's under the curve?
Where, here?
No, there.
Here, yes, this is, see, we already know that this integral right here is going to spit out a negative number. And we know that because it's measuring, this right here is the height of the function. And we know that in this little interval, the height of the function is negative. So it's going to be a negative number times dx, which is a positive number. We're going to be adding up a bunch of negative numbers. It's going to be negative. So we subtract it to turn it back into a positive. We're going to have more time with this. In fact, I'm not giving you any homework over this. All I'm doing is telling you to finish off the partial fractions. And then in addition to the partial fractions, everybody likes bonus, right? Everybody loves bonus. So